Okay, good afternoon. So today we'll continue on talking about the IO. Hopefully, I get to finish this today and move on to the next topic. So previously we talked about the IO subsystem, um, and we defined the difference, a few different interfaces. So let's I believe this is where we left off. So let's talk about one um, more device dependent mechanism and then we'll start talking about the PCIe. So in terms of communication with the CPU, IO devices support different mechanisms. One of the most popular and old-fashioned ways of communicating with devices is through polling. So basically, the CPU is responsible to check and see if the IO is ready or if the IO has finished the job that it was supposed to do. The plus side of this is that um, you are avoiding being interrupted. But then the downside of this is you're wasting CPU cycles. Now compare that to interrupt-driven I/O, where CPU delegates a job to the I/O device and then moves on to doing other tasks. And then once the I/O device is done, it interrupts the CPU, and CPU then gets activated by running the interrupt handler to manage the interrupt. This one, the plus side is that we're not wasting CPU cycle on just waiting and busy waiting for the device. The downside of this is the being interrupted could be annoying in terms of, for example, predictability, right? So if you don't know how many times your device is going to interrupt your processes, then you don't have certainty on the, for example, execution time of your processes. The other downside of this that I haven't mentioned, but it's kind of like implied, is let's assume that you have a device that interrupts, that produces interrupts very frequently. This could potentially introduce a lot of overhead because every time an interrupt is triggered, we have to do a switch. We have to switch the mode and start running kernel code. Now, if this happens very frequently, then at some point you might end up paying a lot of overhead cost. Now, you could actually think about a hybrid model where you basically wait for the first event by using interrupts. Once that event happens, then you can start pooling. This could be very useful for network devices. You could wait, for example, for the first packet. When the first packet comes, you kind of know that further packets are going to be delivered, so then you can start polling. The typical, this is like kind of old-fashioned architecture for connecting different components to the CPU is through the north-south bridge layout. So the main part of this graph is basically at the top where the CPU resides. Now, the CPU is connected to the memory, so the CPU is basically the main part. Memory is the second important piece here. Now, memory has a memory bus. So this bus here is the important bus that everybody in this picture basically shares. Now, CPU is connected to the memory through the memory controller. Now, memory controller is historically called the North Bridge. Now, I/O devices are connected to the I/O controller, which again historically is called South Bridge. So the North Bridge and South Bridge are connected through an internal bus. This was kind of, if I'm not mistaken, this design was by Intel. Early systems, so if this was the motherboard, you had your CPU. Then on the motherboard, you would have your North Bridge, and then you would have your South Bridge. And here you would connect your memory slots, and then here you would go to different I/O devices. So this was on the motherboard. AMD years ago brought the North Bridge inside the CPU. So North Bridge was brought inside the CPU. And then you had only the South Bridge outside. So here you would connect your, sorry, here. Here you would connect your memory slots, and then CPU, and then all the memory devices would be connected to the South Bridge. Now this was revolutionary in terms of performance because, you know, here going in the first one, going from CPU to memory would require off-chip traffic. So you have to go outside the CPU chip to get into the memory. And this usually introduces a lot of overhead, performance overhead. By bringing the North Bridge inside the CPU and putting it on the same chip, this basically speeds up sending requests to memory from CPU, and it actually boosted the performance of AMD processors. A few years ago, I'm not quite sure how many years, but it's, if I were to guess, it's like 5-6 years ago or so. AMD introduced a new architecture where basically both North Bridge and South Bridge would be on the same chip, and this, as you could imagine, really boosted the performance of AMD processors. So the same thing that happened here, where I/O requests would be off-chip traffic, introduced a lot of overhead. At some point, this didn't matter because I/O devices were already slow. So sending requests to the I/O controller and paying some overhead for that didn't matter. But today, I/O devices are extremely fast. They're closing the gap, and they're becoming basically a faster component of the system. So it matters to reduce the overheads of I/O. So bringing the South Bridge on the same chip really did have an impact in improving the performance of CPUs, of basically processors. Okay, so there are, as I mentioned in the previous lecture, there are so many different protocols to communicate with devices. One of the major protocols that we're going to talk about is PCI. So PCI initially was just a parallel bus. But then, you know, parallel buses have their own limitations, and in particular, the most annoying things about them is that they have to be the frequency and the speed of the bus has to be lowered to the slowest device that is connected to the bus, because all the devices on the bus have to understand the packets that are being communicated on the bus. And this requires the bus to have to accommodate the slowest device. So PCIe Express was an extension to PCI, and what happens was that they moved from parallel buses to serial packet-based buses and switches that would allow point-to-point communication, peer-to-peer communication between different endpoints, between different devices connected to the bus. Now, each device would get connected to the bus through a switch, and then this would actually allow the bus to be decoupled from devices. So you could have really fast serial bus, and then you could connect really slow devices to this. But because there is a interface, they go through their own switch to get connected to the bus, then you could again decouple the speed of the bus from the speed of different devices. And then devices could use as many lanes as they wish. So one of the major successes of PCIe and PCI protocol and architecture was its downward compatibility. So what happens was when PCIe Express came in, they didn't change the interface. They went with the same software interface that they had for PCI. And this allowed older devices that worked well with PCI to be able to work on PCIe Express, on PCIe. And this was a major success. Now this, it requires a lot of, thinking and designing and engineering to come up with a protocol that is future-proof. But they actually did it. So they added new features in PCIe, but they kept the functionality of PCI protocol intact. And that really made a huge impact in popularity of PCIe. Now, if you look at the picture in this slide that I'm showing, this basically shows you all the components that I talked about. So you have the switch, different PCIe endpoints are connected to the switch. Now PCIe also allows endpoints to get connected directly to the root complex. It also allows, bridges between different protocols. So if you have another kind of bus that you want to connect to the PCIe, you can put an adapter, put a bridge, and then connect different buses to the PCIe bus. So as I again mentioned in the previous slide, PCIe also allows point-to-point communication. So each endpoint can now talk to another endpoint. So it's a bidirectional communication. The two main endpoints in this figure are the CPU and the memory. So these are also considered as endpoints. So this allows if you're running your driver on the CPU, your driver can communicate with your device. And let's say if you set up a DMA, then your device can communicate directly with memory as another endpoint to write or read from or to the memory. Now, here I'm showing you a snippet of what comes inside a device. So any PCIe device usually has a hardware controller inside. So that's this component. So we have a hardware controller that is in charge of controlling the device. Now, usually you have a PCIe interface. So if your device supports PCIe, it usually have a PCIe interface. Sometimes these are called PCIe engines. Your device, the way to communicate with your device is through control registers. So there are a bunch of registers that are visible to the CPU and to the system, and these are usually used to send commands or read the status of your device, right? There could be many different registers depending on what the device does. And sometimes you see command or data queue buffers. Excuse me. So these are for devices, for example, like display, where you want to send a sequence of commands, or for example, for your GPU. So there are buffers, data buffers and command buffers that the CPU can use to send data or sequence of requests or commands to the device. Now, it's important to talk about registration of PCIe devices. So at boot time, this usually happens when your BIOS initiates the system. So each device, when you power it up, each PCIe device kind of advertises its needs using its configuration space registers. So there are configuration state registers that the device uses to tell the system what kind of registers it has, what kind of address spaces it needs, how much buffers, how much command buffers or data buffers it has, how many registers it has. So this is kind of like advertisement at the beginning when you turn on your system. Now BIOS reads these registers, recognizes what the device needs, and then maps those registers and those buffers to physical address space. And once this mapping happens, we go and write to the same register that the device was using to advertise its needs. We just write to it, and by writing to those registers, we tell the device what the mapping is, meaning that how the registers are mapped to physical addresses. Now, this is important for the device to know, right? Because later on, when you're running, for example, your driver, and your driver is sending commands to your device, basically your driver is using load and store instructions to load and store to certain addresses, and those addresses are the same addresses that these registers are mapped to. Now, you want the device to know that these addresses are associated with the device's registers, so that the device can listen and understand those messages. So that's how it happens, right? We write to the same set of registers, usually base address registers, to tell the device the range of addresses that are assigned to that device. Okay, now in terms of communicating with the device, there are two ways. There is the port mapped way of communicating and transferring data to I/O, and there is the memory mapped I/O. So with port map, the I/O device has its own separate address space, and so they don't share the same address space with the memory. In that case, in order for the CPU to communicate with the device, the CPU has to issue in and out register instructions. So when so for example, when you say out this address, the CPU sends this instruction to the I/O bus, and this is kind of different if you had done a store 0x21. So if you had done a store, this would be sent to the physical address space that is connected to the memory. But if you use out, then you're telling the CPU that this is for I/O. Now, this is kind of like not common in general purpose computers. This is usually used for embedded systems and microcontrollers. What is usually used is basically memory mapped I/O, which is used for PCIe, for example, PCIe devices. So in this one, all the devices share the same address space with the memory. So the CPU always issues loads and stores, and it's just the devices have to know the range of memory addresses that are assigned to them. And if the CPU issues, for example, store 0x, some address f, blah, 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 then depending on if this is mapped to a device or if this is mapped to the memory, the device or memory responds, because both of them are mapped to the same address space. So I got a question: do port map I/O devices have their own memory since they don't use the physical memory? Okay, so when it comes to memory, you have to note that usually you have some on-chip or on-device memory. For example, those registers or those buffers. These are the hardware storage on the device. Now, if the CPU wants to send commands or data to the device, the CPU, for example, uses this out or in to send data to the device using this address bus. Now, if the device wants to talk to memory, usually it happens through a DMA engine, right? So the device talks to the DMA, and then the DMA talks to memory, back and forth. We saw an example of this in, I think it was lecture 2, if I'm not mistaken, when we were talking about the I/O communication. So you have to be careful which memory we're talking about, right? If you're going back to this slide, if you're talking about these buffers on the device, then these are on the device, and CPU uses in and out to read or write to these registers and buffers. Now, if the device wants to read from memory or write from memory, then it has to communicate with the memory, which usually happens through a DMA engine. Okay. I mean, if the device wants to directly communicate with the memory. Otherwise, if the communication is by the CPU to the device, then we just use this in and out, right? So the CPU, for example, reads some data from memory, puts it in a register, and then uses out or in to send or read the data from the device. Okay. Now let's look at an example of memory mapped devices. In particular, let's look at like a typical display. So let's assume that this display has a command buffer that is mapped to this range of addresses, and it has its own data buffer that is mapped here. So this is kind of like a data buffer. The first one is the memory command buffer, data buffer, and then these are command and status registers. So these are registers, so each one of them has a single address. And then these are buffers, they have a range. Okay, so usually, as we discussed, this mapping happens during by the BIOS, or sometimes the operating system does it, depending on the systems. Now, let's assume that you want to send a sequence of commands to the device. So what you usually do is that you use this range of addresses to write those commands to memory. So you just write your data in these addresses. Eventually, once you want the display to execute those commands, you send a signal to this command register to tell the device that, the commands are ready, go and execute them, right? So you can just write to this particular address, this command register, to tell the device that the commands are ready. You might also want to, for example, if this is kind of like you want to render some picture, some image, some video, you also put the data for each pixel in the display memory. And then once you send the address, once you send the go, the device starts executing those commands using the data. And then potentially, for example, once everything is done, this status bit changes to 1 or 0, depending on what it wants to do. Yeah, one thing that here is important, it's kind of like a reminder of what we saw previously. If you remember, when we talked about access permissions, I talked about this particular access, which was write only. So you don't have read access. So this write only access is usually used for these registers, not the status, actually, for potentially for the command. Because the status, you also want to read it. You want to know what's the status of the device. But for the command, it's probably just a read on write only. You just write to that address to send the command to the device. You don't read it because reading happens by the device. Device is gonna read that and does stuff that we don't know. So we don't want to read it. We just want to write to those addresses. Okay, now just a reminder again of what we saw previously in probably lecture 2. We talked about programmed I/O and direct memory access. With programmed I/O, for every byte that is transferred between CPU and the device, the CPU is active. So CPU, uses in and out or load and store to communicate with the device. So this the bright side of this is that it's simple in terms of so this is simple in terms of implementation. It's also easy for programmers to use. The downside of this is that you're wasting CPU cycles. So the alternative is direct memory access, as we talked. So with this one, you set up the transfer, the driver sets up the transfer, the data transfer. Let's say if you want to transfer 1 GB of data to your device, let's say you have a GPU and you want to transfer 1 GB of data and then let the GPU do calculation on the data. You usually do that through DMA. You don't want to send each byte of data using load and store from CPU. Once the transfer is done, the device interrupts the CPU, telling the CPU that the data transfer is done. And the The upside of this is basically we're not wasting CPU cycles on data transfer. The downside is, well, it's a little bit more complicated. It requires interrupts, it requires DMA engines and all of that. Now, the model that we talked about previously assume that there is a common shared DMA engine on the chip that all devices talk to do their DMA. This is usually different for PCIe devices. It's very common for PCIe devices to have their own DMA engine. So these are usually proprietary engines. For example, your GPU probably has its own DMA engines. Actually, not just one, usually but many DMA engines. Your NIC card has its own DMA engine. Your SSD has its own DMA engine. Now, as we discussed in PCIe, each device can have a point-to-point, peer-to-peer communication to any other device, including memory. Now, the DMA engine does whatever the common DMA engine could do. So a proprietary, local DMA engine in a PCIe device can get commands from the driver and then start communicating and sending packets to or from memory. Yeah, and then once the DMA engine is done with data transfers, it can communicate with the CPU through raising and interrupts. Now, let's talk about I/O devices and memory protection. So typically and historically, I/O devices need contiguous range of memory addresses, and this is common. This is actually a trend that is changing. But back in days, you didn't want to make a lot of logic in your device to understand to communicate with the device. So you would just have a base and bound kind of implementation for the range of addresses that the device reads or writes to. And this requires basically contiguous range of memory. So your device would know the base address for its buffers or for its registers, and then a range. So how many addresses are assigned to me from what base. Now, again, historically and in past designs, your I/O could directly talk to memory using these physical addresses. And, again, this is easy to implement. There is no need for any address translation. You're using physical memory address ranges. So very easy to implement. You can achieve really high speed because there's no need for translation. Let's say you're doing a DMA. Your DMA engine knows a range of physical addresses, and it just writes or reads to that range or from that range. Now, the downside of using physical addresses is that it reduces memory protection, because what if the device is a malicious device? Giving the device access to physical memory means compromising isolation. So the device can potentially compromise the operating system, read sensitive data. so on and so forth. And it has happened a lot. It's called DMA attack. It's very commonly used security attack. Usually, I mean, I guess I've seen the modem ones for network cards. So basically, your network card goes and reads memory, you know, whatever it wants to read from memory, and then sends it to adversary using the, you know, using internet, for example, to communicate. It also reduces flexibility, right? If the operating system has to assign a contiguous region of memory to each device, this could potentially create restrictions on how the operating system can allocate memory, and potentially create you know, fragmentation. In new architectures, we have fixed this problem, obviously with the cost. So this green point here, the performance, is the cost to pay. So in new designs, we're requiring, or we are enabling address translation for hardware devices. So basically, devices could work with virtual address instead of physical address, and then those addresses would get translated. Sorry, how can I get rid of this? Okay. So the device would just work with virtual addresses, and those virtual addresses would get translated to physical addresses. Now, if you remember, so this is the architecture previously we saw. So this is your memory controller, memory hub that is connected to your memory. Now, with address translation so far, oh yeah, so somebody said we can't see the entire slide. Yeah, I've already done that. So this memory, main memory, the memory management unit, MMU, is in charge of translating a virtual address to physical address for this, for the CPU. So here your CPU generates virtual addresses, and then MMU turns them to physical addresses. We talked about this in details in the previous lectures. So this is basically address translation. Now, new architectures add the same unit. It's called IOMMU. So this is IO memory management unit that does the exact same thing. So the IO devices generate virtual address, and then IOMMU turns them to physical address. Now this requires, so we talked about how MMU works. So the operating system is in charge of setting up page tables for memory address translation. In MMU, the same happens with IOMMU. So the operating system has to set up page tables for IO devices, saying what ranges of physical addresses each device has access to. Or if, for example, you're allowing a device to do DMA to some process, you might want to map the physical address that is mapped to that process to the same device, so that the device could just write directly to the process's memory. So that's possible. So basically, the possibilities for IOMMU is countless. You could, you know, just make the device to write to kernel memory, and then kernel would write that data to the process, or you could just allow, the same way that we did sharing between processes, we allow two processes to share the same physical address. We can make a process and a device share the same physical address space. This is, for example, if you're familiar with RDMA, I'm not going to explain it, but if you've heard of it, that's pretty much what happens. So your NIC is able to read data from your processes address space or write data to their virtual address space. So operating system basically sets up the page tables, and the device uses virtual addresses, and then the translation happens in IOMMU, and this actually brings protection, brings back flexibility. Now the operating system doesn't have to give your device a contiguous range. All it needs to do is give it contiguous virtual address range. When it comes to physical memory, you can do whatever you want because you're doing mapping. And again, protection is there. So I got a question here. Do I/O devices get access to the same virtual address range as the CPU? I.e., does the size of the virtual address range change for I/O devices compared to CPU? No, all of them are accessing the same memory bus. So everybody uses, for example, in a 64-bit system, everybody's address is between 0 to 2263. Or 2 to 64 minus 1. Now, the only question is whose virtual address the device has access to, right? You could, and again, as I said, the possibilities are countless. You could potentially create virtual ranges for your devices. You could use, the same virtual address range that you're using for a particular, for example, process. This is actually an active area of development in systems, in operating systems, in data center systems. So by playing with the capabilities of IOMMU, you could potentially do things that were not possibly implementable in the past, because now you can do this mapping, and it brings a lot of capabilities with protection, obviously, right? Because previously you could do whatever you want, but you didn't have any protection. Now you have protection, so you could do things that were not possible in the past. Okay. Again, I really did just scratch the surface here. This is an area we can have a course on. We can have a advanced operating system talking about all of these issues. I'm just introducing some of these concepts now. If you guys are interested, you can follow this, read them by yourself, or unfortunately, we don't have any advanced operating system course, at least in ECE. I know CS has advanced operating system courses, but I'm not sure if they cover these topics. But these are really interesting topics that you can follow, and an area that is evolving very fast. Okay. Now, when it comes to PCIe devices, this memory translation could pose some difficulties. The first difficulty is that there is this capability designed in PCIe protocol that allows devices to bypass IOMMU. So if you remember, for CPU, for MMU, we had TLB. So this translation buffer, look-ahead buffer that we had, which we would cache virtual to physical address translations. And by caching those translations, we would avoid going to page tables. Now, when it comes to IOMMU, the device itself could implement its own TLB. So the device could cache address translations. So, you know, that you have to talk to this virtual address range. You go through IOMMU and you get your translation. You could cache this translation. And later on, you can go to IOMMU and say, okay, I don't need the translation. I already know where in physical memory I should go. Let me go. And PCIe protocol would allow this bypass to happen. So that's one thing. This could potentially pose some risk, in particular if the device is malicious. It could just deceive the IOMMU by showing that, oh, I know this translation, but then go and write or read from other addresses. The second problem is that PCIe protocol allows devices to talk to each other. So forget about memory. One device could send packets to another device, and potentially you could go and write to the command registers of some other device. So one device starts controlling another device. And again, if your device is malicious, this could happen. Now, fortunately, both of these have a single solution. It's called access control service, which was introduced in PCIe protocol that would basically limit both of these two problems and communication. So first of all, it would, I think the mechanism to fix both of these problems is to force all communications to go through IOMMU without exceptions. And as long as all communications go through IOMMU, and then the operating system can control IOMMU and give it necessary instructions on who can access to what memory or address ranges, both of these two problems would go away. So first of all, we don't allow caching of virtual to physical addresses by each device. This obviously comes with a performance penalty because we are not allowing, the whole idea of caching these virtual to physical addresses to have a better performance. Now we're not allowing it. We still could have this TLB implemented inside IOMMU, but we're just not allowing each device to have its own cache. And also, we don't allow point-to-point communications that don't go through IOMMU. So if one device wants to talk to another device, it has to send its request to IOMMU, and then the request gets routed to the other device by IOMMU. And now if this access is not allowed, then IOMMU can refuse the access. Okay, so the next topic that I am going to skip over is I/O performance concepts. So unfortunately, we don't get to talk about this in details. I'm going to just introduce concepts that will be needed later on, but I'm not going to go deep into analyzing this. So usually when you're talking about I/O performance, you're talking about latency of accessing your device. So the latency of an I/O request is the time from when the request was generated until the request was answered. Now, this is very abstract, so let's bring it down to a particular architecture. So let's assume that the source of I/O requests is the device driver. So the device driver generates requests. Let's assume that the device itself has some queue for all these requests. Obviously, this is very simplified version. In reality, the request first gets queued inside operating system in I/O request buffers. Then the the request is sent eventually to the device. The device itself could have queues. For example, your SSD has a queue of requests. Your NIC could have a queue of requests. So we're eliminating all of them and just assuming that there is only one request queue. So all the requests go to the same queue. And then eventually the I/O controller inside the device reads your request and processes the request and sends a response. So with this simplified model, the latency is from the time that your request is generated until your request is done out from the I/O controller. So that's your latency. The throughput is the rate of serving I/O requests. So we're going to look at the controller and see how many requests per second, for example, the controller can perform. And then the overhead is basically the waiting time inside this queue. So from when the request was generated until the I/O controller starts processing. Until I/O controller starts transferring the request. Transferring the data for that request. So your device has a peak throughput. This is the maximum rate of data transfer. Now, this usually depends on multiple factors. One of them is how fast is the bus, the data transfer bus. For example, with PCIe version 5, you get to go all the way to 3.93 gigabytes per second per lane, and you usually have 16 lanes. It also depends on your device's bandwidth. So how fast the controller can answer the requests. For example, if you had those old disks, the hard drive disks, where you have a disk that rotates, then there is a limit on how fast you can read or write from those disks, depending on how fast those disks are rotating. So overall, your peak bandwidth is limited by the whichever of these that is going to be your bottleneck. So if your bus, your data transfer bus is slow, then that becomes your bottleneck. If you have a really good data transfer bus with high bandwidth, but then your device is slow, then your device becomes the bottleneck. You also have an effective bandwidth. So this one is basically what is observed of your system. So this is the rate of data transfer for I/O requests, not the max, but what actually happens in reality. Now, the effective bandwidth is something that really depends on, for example, how frequently you're creating requests. For example, if you're not sending any requests to your SSD, your effective bandwidth is 0. Your maximum bandwidth could be some number of gigabytes per second, but it's just you're not using it, right? So effective bandwidth is always less than the peak bandwidth, obviously. Now, what is the kind of limiting factor in your bandwidth? The limiting factor in your bandwidth is latency. So when you have high latency for each request, you're spending so much time on overheads, and that reduces the bandwidth you have. You can process less amount of IO requests. Now, a mathematical definition of latency is the overheads that you pay. So this is the time that you spend not doing anything useful, maybe waiting on the queue, for example. Nothing is happening. This is an overhead. And then at some point you start answering the IO request. Let's say that your your device controller starts transferring data. Let's say this is an SSD. You have eventually looked at the request. It needs to read some flash page, which we will talk about. So now your device controller, your SSD controller starts transferring the data. Now, how long does it take for the data, if you have requested for n bits or n bytes? How long does it take for the data to be transferred? Well, you're limited by your peak bandwidth. This is the maximum bandwidth you have to transfer your data, right? So overall, it takes n divided by your peak bandwidth to transfer your data. So your total latency is the time you waited plus the time it took you to transfer the data eventually when you process the request. So this is your total latency for transferring n bytes. Now, what is your effective bandwidth? Your effective bandwidth is the amount of data you transferred divided by your total latency. So you can now use these equations to analyze your bandwidth. So the latency, basically, we can just, I'm rewriting everything. I'm using O for overhead and P for peak bandwidth. So I'm rewriting the equation. The latency is O plus N divided by P. Now, effective bandwidth is N divided by O plus NP. So you can just move these variables around and get to this equation. So your effective bandwidth is your peak bandwidth divided by peak bandwidth times overhead divided by N plus 1. So let's say you want to, if you set N to your overhead times peak bandwidth, then your effective bandwidth becomes half, for example. So this effective bandwidth, as I said, depends on how much data you want to transfer. And again, this is, you can confirm what the example I said. If you don't send any request, then N is 0. So effective bandwidth is 0. You're not moving any data, so your effective bandwidth is 0. Then you start increasing N, and then your effective bandwidth changes. Now, for a particular N equal to O times P, you can verify that your effective bandwidth becomes half, meaning that your effective bandwidth is half of your peak bandwidth. Now, if you draw this effective bandwidth for different peak bandwidth and different N, you get graphs like this. So this particular graph that you're seeing, on the x-axis, I have the size of data. So this is basically your N, how much data you're transferring, and on x-axis, I have my latency. Sorry, on y-axis, I have the latency, and on y-axis, the other side, I have the effective bandwidth. So the red curve is effective bandwidth, or EB, and the blue curve is your latency. Obviously, latency also increases by n, right? Latency is also a function of n, is a linear function of n. As you can see, it's O plus n divided by p. So that's the blue curve. Now, this particular example is a slow device with 1 gigabit per second peak bandwidth. So let's assume that the overhead is 1 millisecond, and the number of bytes is this many. Oh, sorry. Yeah, so this is the overhead. This is O, and let's assume that n equals this guy. Oh, sorry. Okay. What is happening here is I am trying to get to this half maximum, right? So if this is my effective bandwidth, getting to 50% of it, which is here, somewhere there. No, actually, this is 50, 60. I guess the best way is to use this equation, right? Oops. What just happened? So I'm using this equation. I'm putting for n 1 millisecond, and then I'm multiplying this with 1 gigabit per second, and then dividing it by 8 bit to get 1 byte, and this gives me 125,000 bytes. So at this if the request size is 125,000 bytes, then my effective bandwidth is half of my peak bandwidth. Now, if I get a better device, so actually, if I get a worse device with a higher overhead, 10 millisecond as overhead, then I need higher amount of data transfer to reach the same half peak bandwidth. So if I increase the overhead, then to get to high effective bandwidth, I need to send more data. And as you can see, both of these two graphs, these red graphs, your effective bandwidth increases as the amount of bytes that you want to transfer increases. So as you move along the x-axis, your effective bandwidth increases. Now, if your device is fast, then this increases faster. Eventually, it plateaus. If your device is slow, this increase is also slow, as you can see. Okay. So let's see. Yeah, I'm gonna move over these. We're not gonna be able to talk about the rest of these guys, unfortunately. Otherwise, I won't be able to talk about Okay, so again, we just introduced some concepts in I/O performance, but then we didn't, unfortunately, have time to dig deeper. So I leave that to you if you're interested. Just look at the slides; they should be self-explanatory. Now, The next topic I'm going to start talking about is the storage devices. So among all the devices, for some reason in operating system courses, we pick traditionally the storage device. There's no particular reason to do so. I think you could talk about GPUs if you were interested as a device. You could potentially talk about NIC devices. But for some reason, we talk about storage. I mean, it's kind of like the reason is because of data storage. Like the data is stored somewhere, so we want to talk about the device that stores data. But you could also talk about devices that process data, for example, your GPU, or devices that transfer data, like your NIC. But anyhow, so let's talk about storage devices. In particular, we're going to talk about two different generations of permanent storage. We're going to talk about a little bit about magnetic disks, and then we'll just talk about flash memory, which is a more recent technology for permanent storage. So the magnetic disk is the previous generation of permanent storage, because before that we also had other technologies to store data. Now, when you're talking about magnetic disks, these are still relevant. So, for example, there was a paper from Google, if I'm not mistaken, that Google is using these disks to store their archive, for example. And it's important to because these are cheaper compared to, for example, SSDs, and they have more capacity again compared to SSD, and they're cheaper. So there was, like, Google had done some optimizations in using these devices efficiently for archiving data. But so again, my guess is in 5 years these would not be relevant anymore and nobody would talk about them. But until then, let's talk about them. So the magnetic disk usually consists of a bunch of platers. These disks in this figure, so they're stacked on top of each other and they're rotating. Now, the way to read and write from these disks is through these heads. So you have this arm, and then a sensor that reads from the disk, and this usually on the plater, on both sides of it, you can store data, read and write. Now, these arms go back and forth so that you can cover the widths of your disk, so that the hand goes back and forth from the inner circle of this disk to outer circle of the disk. Each circle on the disk is called a track, and we usually divide each track to sectors. So basically, each circle is a track, and each piece on this circle is called a sector. So I don't know if you remember, like, I don't know if you have had any experience with bad sector errors in Windows. So this was telling you that one sector or bunch of sectors on your hard disk have been damaged and you can't use them, and that would give you a bad sector error. It's now a history. So does each plater need its own read-write head? How thin is each plater? Yes. So each plater has its own head. So I guess I can actually go with the slide. So the unit of data transfer is sector. So we read or write from or to these sectors. Each track is about I mean, this depends on technology, right? But usually around 1 micromillimeter. Sorry, what is that? 1 micrometer. If you want to have a sense, this is like twice as large as a wavelength. That's how thin each track is. So in a typical 2.5-inch disc, you have more than 100K tracks. So these are really, really thin tracks. Because they're very thin, there is always an error that the head might read from a neighboring track. So that's why usually you have these guard regions between tracks. So you put some space between tracks to minimize the error. So on the outer circles, outer tracks, you have more sectors, obviously, compared to inner circles. So sometimes you might actually forego using the first half of your disk. So, you know, the area here compared to the area here outside, you might actually not use this first one and just use the outer half. Yeah, I guess I talked about that. Okay, so let's look at the overheads of accessing data on your disk. Let's assume that the arm is located here. So let's say that the head is on this particular position. It's the original position of the head on this particular plater, and you want to read this sector in the outer track. So there are two movements, and let's assume that your disk is rotating. So what's going to happen is first you have to seek to the track that you're interested in. So the arm has to move back to be placed on the track that this desired sector resides. So that's the first move. And then you have to wait for the disk to rotate so that the sector that you're interested comes under the head. So the two movements, one is to move the arm, and second to wait for the rotation to bring the sector to us. So there's a seek time, which is the time that it takes to move the arm, and there is the rotation latency, which is the time that it takes for the sector to become available under the arm. And once this happens, once the sector is under the head, then you can start reading and start transferring immediately afterwards. So if you want to put all of this into the formula that we saw, your request comes, let's say by your device driver. It gets queued, as I said. Usually inside the operating system, you have this IO requests. Then it's sent to the device. Let's assume, as I said, this is just a simplification, that there is only a single queue. In this slide, I have assumed that this is a software queue. You could potentially assume that this is a hardware queue, or both. You might have, in reality, it's both. You have a software queue and then a hardware queue. Then your controller receives the request eventually, spends some time to produce your result. So overall, your latency is the time you spend in the queue waiting. Once that's done, you have a controller time, the time that it takes for the controller to decipher this request, to recognize which sector it wants, to turn that request into commands for the ARM and all of that, to recognize and identify the sequence of event that should happen to reply to this request. Once that is done, then you have to pay the seek time, the rotation time, and then eventually your transfer time. So that would be your disk latency. Okay, so how much time do I have left? 4 minutes. That's sad. Let's for now ignore the queuing and the control time. Let's assume that those are 0. The requests are not going to wait at all for just simplicity. We can always add those back. Let's assume that the average seek time is 5 milliseconds. Now, why do I have average? Because obviously, if the head wants to just move to the neighboring track, that takes almost 0 time. Like, it's very fast. It's just a single slight movement to another track. But let's say if the head is in the inner circle and it wants to come to the outer circle, then that would be a longer seek time. Now, on average, the seek time is basically half of the width of your disk, right? So sometimes you go from the inner to outer, sometimes you're just moving between neighbors. So on average, you're probably moving half of this distance. So let's assume that there is an average seek time, and it's given to us by 5 milliseconds. Usually, when you buy these disks, they have this RPM, which is rotation per minute. How many rotations you have. So let's say you have 7,200 rotation per minute. You can turn that to time for rotation. So for each rotation, how long does it take? Well, you have these many microseconds per minute, and then you have these many rotations per minute. So if you divide these two, you get something like 8 milliseconds for each rotation. So each complete rotation takes 8 milliseconds for this particular RPM. The higher the RPM is, the lower the rotation time becomes. Now, let's assume that your transfer rate is 4 megabytes per second. So this is basically your peak transfer rate. Let's assume that each sector is 1 kilobyte. Then how long does it take to transfer a single sector? Well, you want to transfer 1 kilobyte. Your transfer rate is 4 megabytes per second. You just divide these two. That gives you something close to 0.24 milliseconds just to transfer a single sector. I know I'm hitting the time, so I apologize. I'm going to just finish this slide and then end the lecture. Then, so if you want to read a random sector, you're going to pay the seek time. You're going to pay a rotation delay. An average rotation delay is again half of the rotation, right? On average, you're going to have to rotate half of the disk. Again, average, because sometimes you have to rotate the entire disk to get to the sector that you need. Sometimes you have to rotate just a little bit to get the sector that you need. Sometimes you have to rotate half. On average, we can assume that the average rotation time is half of a full rotation. So if a full rotation takes 8 milliseconds, average rotation takes 4 milliseconds. And then you have to transfer that single sector. So this gives you approximately 10 microsecond latency. Now that you have the latency, you can actually have your bandwidth, effective bandwidth. So you transferred 1 kilobyte in 10 milliseconds. That's an effective bandwidth of 100 kilobyte per second. Again, effective bandwidth is the data that you transferred divided by the latency. So the data that we transferred was 1 sector, which the size was 1 kilobyte. It took us 10 milliseconds. So you can then see what the effective bandwidth is. In this case, the effective bandwidth would be 100 kilobyte per second. Now, let's assume that you want to read a random sector on the same track that your head is currently. So this means that you're not going to pay any seek time. So you get rid of the seek time. You only have to pay an average rotation delay, which is 4 milliseconds, and then a transfer time. That dramatically increases your effective bandwidth. It makes it twice as large, right? Because now you're spending half of that time. You're not seeking the arm anymore. So the arm movement has gone out, and this gives you an effective bandwidth of 200 kilobyte per second. Finally, if you want to just read the next sector, then you can assume that there is no arm movement, and the rotation is just, it's the next sector, so you're not going to wait anything for the rotation as well. So you're just going to transfer, and that gives you the best transfer, the peak bandwidth, basically. So it makes your bandwidth equal to your peak bandwidth if you just were to read the next sector all the time. Obviously, because we're just getting rid of the overheads, which in this case was the seek time and the rotation time. So this example shows you that, you know, putting data smartly on the disk, or doing some sort of a smart request management. So if, let's say, you have a list of requests, and you can potentially sequence them in such a way that minimizes the arm movement and rotation, then you can get the highest bandwidth. So that's why a lot of effort has gone to really optimizing data placement on the disk and control design for disks to do a smart scheduling of requests, which we'll talk about in the next lecture on Thursday. So thank you so much for sticking around. We'll see you on Thursday. Take care, be safe, bye.